So now we're going to look at two key network protocols, and that's ARP, as we'll find any presence of anyone communicating over the network typically starts with an ARP request and an ARP reply. So it's often the first place that we would look for any type of activity. When a computer boots onto the network, we'll see ARP activity. When a computer tries to connect to the internet for the first time, we also see ARP. So ARP is a continual protocol that's in use on our networks. Then we'll look at ICMP, which is really a debug protocol, and we'll see how that's used to be able to trace routes and to be able to find if hosts are alive or not. Okay, so first let's look at ARP. And ARP is such a key part of the internet. It's a silent protocol, but it really makes the whole of the internet work. And the reason for that is that ARP is responsible for that last resolution of the physical address. So in the first part of the journey, we need an ARP to discover the gateway, and in the last part, we need the gateway to discover the MAC address of the destination. So with ARP, we don't need any registration of physical addresses anywhere on the internet. We hope that ARP will be able to resolve the physical address of the machine that we're trying to talk to. And ARP is also used for intermediate steps to be able to discover the MAC addresses of any intermediate nodes. Okay, so this shows a basic example. So in this case, here we are here. And what we are looking at here is that we want to get out of the network. So we actually have the gateway address. So in this case, it's 192.168.75.132. So we obviously don't know what the MAC address is, but we want to be able to communicate with it. So what happens is that the ARP sends out a request for the whole of the network. So we define a network as an area bounded by a router port. So every computer on the network that is connected to a switch, it could be other switches, that is bounded by this port here, will actually hear the request for that IP address. So ARP sends it out and it's received by all. It's a broadcast, and we use all Fs for the MAC address for that. So it goes to all the hosts on the network, including the router port in this case. And then the machine which actually has that address will respond back with its MAC address, but only to the node that actually sent it. If we're using a switch, if we're using a hub, then whoever's on the hub will actually receive the message back. But in this case, only the host that actually requested the MAC address will actually get it back. So once it receives it, it then updates what's called an ARP cache, and so it doesn't have to send the request out again could be for several minutes, and it can keep communicating. So when a machine is sending over the internet, it will then send over it will use the physical address of the gateway and the destination IP address of the node. So in this way, we can actually discover the network dynamically without having to set things up. Good thing is we could change the network card on the router here, and hopefully eventually all the machines will be able to discover the new address. So it's an amazing little protocol, and it's really the workhorse of the whole of the internet, and allows the thing to be so dynamic. But it can cause many problems. One we'll look at later is we can have what's called ARP cache poisoning. Somebody could poison a cache here so that it went to the wrong gateway. So instead, someone could poison it, and there could be another gateway of an intruder, say with a wireless network, and it might take the data packets away and spoof the gateway. Okay, so that's the ARP. and what we'll do is we'll have a little look at what a trace looks like. So in this case, this machine sends out a broadcast, that's all F's as we see here, and we put our own MAC address in here, and it's an ARP request. It says who's got this IP address, and then what should happen is that the reply comes back, and in this case it's a directed address. Okay, so we can see here 2 physical addresses, so it's not broadcast back, it only goes back to the machine that sent it, and it actually says it's at this address here. What should happen next is that the ARP cache will be updated with that address. We'll just have a look at that. So ARP, there's an example of our ARP cache, and what we should see, hopefully, is that in this case this is my address here, and I'm on a private network behind a wireless NAT device, and we can see it's discovered that MAC address of the gateway. It's also discovered some other addresses, and we can see this is dynamic, which means that this has been learnt rather than static, which means that it's actually hardwired into the cache. In some secure systems, it can be common that the entry into the ARP cache is a static entry, so that no one can actually change it, or it stops it from being rediscovered. Okay, so that shows an example. So what we'll do is we'll have a look, and we'll see that in all of the traces that we have, ARP is often the first sign of anything. So there you go, there's ARP request and reply. We see again, every time that we really look, if we're connecting to something, we'll often see the standard signs of an ARP request and an ARP reply. So what we'll do is we'll have a look at this one here. Okay, so you can use this page here to be able to look at some of your details. Okay, so you can see there's the Ethernet details, and there's the ARP. So Ethernet in this case is carrying ARP. It's carrying ARP by defining the field. So it's a layer 3 protocol, because it's carried within an Ethernet frame. So let's have a look at this. Okay, so this is a very simple example of really just accessing a web page. Okay, so in this case, actually the host is on the same network as us, so we send out a broadcast for the host that we want to connect to. So we can see our ARP request here. Okay, and hopefully we should see in our Ethernet, our destination is all Fs. And in this case, what's happened here is that the computer at 132 has replied. So you can see there its end address is A3. So what we should be able to see, because it's on the same network, and we're not using we are using the gateway in this case, is that there's the destination address here on the same network. Okay, so we've discovered it. It will be updated in our ARP cache, and we don't have to rediscover it for several minutes. It depends on the operating system that we're actually using. Let's see if we can find one that actually has a gateway. So I'll have a look at this one. Okay. So in this case, we're discovering the gateway. So you can see here we're at 192.168.0.20. and the gateway has been set up as 0.1, just like the same as on my machine just now. And now we're discovering the gateway, and the gateway has an address of 8C. So now look, when we now communicate with the remote web server, which is at 91.203.99.45, let's have a look at the destination MAC address. And look, it's 0C, which means that we're communicating with the gateway address. Okay, so it's important that we discover what that address is, and then once we get that, the data packets that we send out will have, if they're going destined for the internet, will have that MAC address of the gateway, and then the destination address of the machine, the host that we're trying to connect to. In this case, it's that. Okay, so what will happen is that the data will travel over the internet, and then when it gets to the last device, the last router, then we should find that there will be another ARP request for that address, and then that gateway port will be able to resolve that back again. Isn't that magic? Okay, so it's a very, very important protocol, and it really makes the whole of the internet work. So IP and TCP might think they do great things, but really we've got to say well done to ARP. So now let's look at another protocol which is used typically in debug applications and for tracing the route, and that's ICMP. With ICMP, we have a simple request and then a reply back again. So if we want to find if a host actually exists and is alive, then what we can do is ping. We ping it, and for our ping we actually send an ICMP request, and we might send multiple ones. We might send 3 or 4, so we send a sequence number so we can match the reply back, and then we send some data. So in Windows, this is what the data that's actually sent, and then if the machine is alive or our ping is allowed to transverse to that host, then we'll get a reply back. So in this case we have a reply, type 0 as an echo reply, that's the sequence number, and again we're replying back with certain details. So the 3 main things that messages types we'll actually see are a 0 or an 8 for echo request and echo reply. So we'll see an 8 going out and then a 0 coming back. So you can see here there's an 8, that's a ping request. And then some of the messages that we get coming back are destination unreachable. Destination reachable is normally when a ping has been blocked on the way, and a redirect. We can also get, when our messages come back, we get what are called type 3 codes, and the type 3 code will actually define in more detail why our ping has not been successful. Okay, so in this case, if we get a 3, then it might be the network's unreachable, it's barred, or it doesn't exist, or the host is unreachable. It gives us more detail here. Along with ping, what we do is we can use what's called traceroute, and traceroute will allow us to see all the routers along the way. We don't see any switches at all, we only see the layer 3 devices. So in this case we send out a ping. We set the TTL to 1 in this case, and then the ping is set to a destination, this address here, and is sent along the line. Eventually the ping will actually time, the TTL will be reduced and will be deleted. So you can see what comes back. Each of the devices on the way will actually reply back with their IP address and the domain name, and then we can get an idea about the basic timing that it takes to get to each node. In this case, we can actually find out the basic performance of the link. In this case, one of the nodes at node 2 hasn't responded back. So our local device, our local port has responded back, but this next router hasn't, and then along the way the other ones have. Often what we find is that the ping will work up to the edge of our corporate boundary, and then inside it then the ping will be not allowed. Okay, so let's look at our network traces again. It's a basic ping. Okay, so in this case we can see here we're ping, and what we're doing is pinging it 1, 2, 3, 4 times. So often when we ping a host, we will ping it 4 times. In this case 4 times gives us the TTL and the time and so on. So let's see the TTL value here. So you can see it's 128. Okay, so you can see it's been decremented quite a bit, but it gives us at least an idea of the response times. Okay, so let's have a look at the trace route. So trace route, what we do is that we try and resolve a route along the way to get to a destination. So there's our gateway. This is where we're trying to get to. And we can see the first router on the way is giving us a timeout, and then we go through the hops along the way to take us through our network to get to our destination. And let's have a look at this in Ubuntu. Okay, so there's our ping. So anytime we can start Wireshark. And put it as a background task. Okay, let's try that again. Okay, so we can capture it, and we can see this is our virtual adapter here. Okay, so there's our ping there. And you can see that there. Hopefully if we ping something that we haven't discovered before, then we should see our ARP happening. but really ARP happens at the start of our communication. So the other tracing tool that we have is trace route. And we can see this should give us the same reply back as we get from our Windows machine here. Okay, so ping and traceroute are two important protocols that we can use. So really this presentation has given us an overview of two of the key protocols that we use. ARP, we can see especially, is so important on the internet, and ICMP.